So what I want to do now is sort of focus on my main conclusions about the surface waters and then about the forests. Now I'm a little nervous here because Joe Karakes is here, and Joe Karakes is one of the fathers of some of the theory about how lakes develop and so on, but I'm glad he's here. Anyway, we have 3 lakes here in the system. They're quite different lakes, and this is some old data, and you can see that the Sandy Lake is by far the largest. It also is much deeper than the other ones. What else about it? Yeah, the retention time is that means, yeah, these flush much faster. This one flushes much slower. This shows you some of the this is from 1984, I think. These lakes are towards the alkaline side, I mean higher pH. Jack Lake, I mentioned, that's that kind of boreal type lake, very acidic. Conductivity is something I always look at. Jack Lake is very low conductivity. These ones have higher values. Talk more about that. And these have much more calcium, which is what affects a lot of the species and so on in it. Yeah, and then these are some data I got last year, which show the same trends between these different lakes.
What does calcium do? Does it make it more acidic or more basic?
Make it more basic, but it's also an essential nutrient for things. So there is quite a detailed study done that was conducted on the Sandy Lake watershed and on what's known about the water qualities and so on. This is the Sandy Lake watershed final report study, the ECOM study, which is really quite a thorough study. Had some big issues with it that have been registered, but was quite a thorough study. And it was intended to represent our current understanding of environmental conditions, application of the phosphorus model, numerical narrative of how development may impact water quality. We identify several methods that can be utilized to mitigate water quality impacts. So that study is available as a backdrop, and here are some of the guts of what it shows. So this shows you the total phosphorus, and this is all based on stuff that Joe and other people did years ago as a predictive model. When you go from oligotrophic, which means nutrient poor, and nutrient poor in lakes is good. It means you don't have lots of algae and so on clouding up the water and consuming the oxygen. Generally, that's considered a desirable condition. This is where it gets higher nutrients, and then eventually fills in with aquatic weeds and so on and so forth. And the aquatic people found that they can relate this overall condition to the total phosphorus. It's a measurement they take from the water, and when ECOM looked at the historical data, they could see that the lake had generally moved from oligotrophic to mid-mesotrophic between 79 and 2012. So that's the historical thing. Here's what they say are their water quality objectives and early warning values. And my problem with this is this. They're saying that when they develop it, this would be their objective, to maintain it in this level. My problem is why wouldn't it be to move it back to oligotrophic? Because that movement here represents the effect of urbanization, and especially with climatic warming and decreased solubility of oxygen and so on, we need to move these lakes wherever possible backwards. So to me, and this is not discussed in the report, it's just stated, that's our objective. So, just looking at that again, as I say, kind of an outsider looking at it, that raised a flag with me. Now, in a sense, this is a kind of surrogate for estimating what's really happening in the lake, and a lot of what you're trying to predict is what's happening to oxygen, especially in the deep waters. And the idea there is that as you have higher total phosphorus, there's more productivity, there's more stuff to sink down and consume oxygen in the deeper waters, and then make it go too low for the salmonids. They need relatively high oxygen concentrations. So the real measure of what's going on in the lake really is not total phosphorus, but is oxygen and temperature. And so I did a set of profiles in 2017 with Derek looking at temperature, electrical conductivity, and oxygen. And we did this at 3 locations. The deepest one, this is Ed Glover's map here, and then we did one site down here. And this is a typical stratification for temperature. Okay, this was done I think in October. I couldn't get this equipment earlier. So you have a relatively high temperature here. You reach what they call a thermocline, and it goes down. So you're going between 17 degrees here to 6 degrees in the bottom. This is where the salmonids like to be. I'll skip this one for a second. Then oxygen does this and goes down here. So you're getting oxygen consumption in these lower waters. This one was surprising and not surprising. Conductivity is essentially a measure of your salt content. And if the lake's relatively pure, you shouldn't have this. But what happens here is when you go down to 6 to 7 meters, at the same point that you're getting this decline, you're getting an increase in conductivity. And that's a matter of concern. It means that you're getting salts accumulating in the bottom of the lake, and at some point that can increase the stratification of the lake and reduce oxygenation. But also it's a kind of indirect indicator of urban input into the lake, and that can mean organic stuff going in and consuming oxygen. So those are things of concern. And I hope I'm not way oversimplifying this, Joe. Now the other thing I did, as I said, I always carry these little meters around with me, and I would just, when I found a stream or something, I'd measure the electrical conductivity, I'd measure the pH if I had the meter, and measure the temperature and so on. So doing that kind of measurement, I could get some ideas of essentially where the dirty water is entering the lake. Conductivity tells me that. So, and these kinds of areas have very low conductivity, 27, 22, 45, and so on. Get into the lake, we get up values around 170. Now, historically, the oldest values are around 50. So that represents urbanization influence. Where is it coming from? A lot of it's coming in this stream down in here. That's where we're getting high values here. So that's kind of how I use those simple measurements. And this kind of integrates some of the different measurements. So first of all, oxygen. How much oxygen do we need? Am I looking? Yeah. This just shows you the oxygen requirements for protection of aquatic life. Yeah, for warm water life, cold water life, these are the salmonids, these are the other types of fish species. These ones need more oxygen than the other ones, and it shows you the critical values. Now there's very little historical data on oxygen in the lake. There is one study from 1971 where they measured the oxygen at 18 meters, and it had a value of 5 milligrams per liter. When we measured it, it was 2.25, and that is down below these guidelines. That's the problem. That oxygen level in the lower parts of the lake is down into critical levels. So it's a matter.
What is a critical level?
Well, it's going to be in this area here.
Oh, okay.
In this area, in this general area, and this is close to it. This is definitely down where you don't want it for salmonids for sure. So I'm just saying, and that's just one measurement. You can whatever it is, but it's a measurement. You can do all the measurements of phosphorus and models and everything else, and you go out and measure the oxygen.
There's a lot of that because of the dead trees and stuff that was put in the clear cut.
Some of it, it's probably more. It's just organic material coming into the lake by Thompson's Brook. That's the big problem. And then pH, historical pH and conductivity. And the thing what I'm kind of arguing is that you have to be careful how you do it, as I'm sure Joe will tell me, but you can kind of use conductivity as some indication of, in general terms, how much garbage is going into the lake. So here are historical values going from 1955, 1971 up to now. And the big changes are roughly from between 1980 and 1985 onwards, going up. And then these are data for HRM lakes. They used to do these synoptic surveys. And this is it's the same thing, electrical conductivity, but for a whole series of lakes. Sandy Lake was relatively low down here historically, meaning a relatively clean lake. These are the dirtier lakes. This is a relatively clean lake, but going up. Okay, so all I'm arguing is that you can kind of use that as a surrogate. It's just data that we have to look at what's going on in the lake, and it's a matter of I'm suggesting it's a matter of concern. So then the question then becomes, where did I go here? Sorry. Where was I? I was there. No, I was here. Yeah, then the question is where? So I showed you this map before. These are the surface waters going into Big Sandy Lake, and then as sort of measured the conductivity of all of these lakes and so on to try and get an idea where the just called dirty stuff for now is coming from. So these are electrical conductivity values around the edge of the lake down on one day with Derek, the yellow one here. And you can see a big spike down here around Johnson's Brook, huge spike. So that's where the stuff is coming from. It's coming mainly from down here. And with that, and a lot of other measurements that I did of this sort show the same kind of general thing. Where you have waters flowing from intact landscapes, you have very low conductivity. Where it's coming from the more settled areas, you have the higher values. And then this fall I realized I hadn't really looked enough down here. This is where Johnson's Brook comes into the lake. I want to know what's going on here. And then we know that there's a sewage treatment system upstream here that comes in down here. So I went out and measured electrical conductivity values in some of these streams. And anyway, the surprise, this is a 125 coming here. That's the one that carries some sewage effluent. And at this time, there was a lot of water flow. The streams are really full. These values would likely be much, much higher when there's lower flow. This is the one that surprised me. Right across here, this is the road to the dairy here. Coming out of here, out of this construction area and some homes and stuff down here. This water looked bad. It was cloudy, it was full of stuff, and didn't look good. It had very high electrical conductivity. And that area, as far as I could see, wasn't identified in the ECOM study as an area of concern, but I think Karen told me that Sackville River people did identify it some time ago. And this is the area I'm talking about here. And this is the actual culvert here, and it was really mucky looking stuff coming out of there. Now, one of the things that I like to use also as a kind of complement to that kind of looking at those types of things are the aquatic plants. I've been it's partially a hobby of mine, trying to get to know them and looking at them and so on. And one encouraging feature is that the major fringing aquatic plant around most of Sandy Lake is the bayonet brush. And bayonet brush seems to be generally associated with more oligotrophic lakes. Where you get up around the inlets and so on, you get more types of aquatic plants characteristic and more inputs. But one thing I'm sort of suggesting is that it's a good idea to keep an eye on what's happening to some of those aquatic plants as some kind of indication of what's happening to the system over. I'm not nowhere near it. System over time. So.